In this video, we're taking a look at how finite state machines can be encoded in Verilog. We will look at both Moore-type finite state machines and Mealy-type finite state machines. Verilog does not define a standard way of describing a finite state machine. So we have to basically put together a couple of flip-flops and use some glue logic in between, some combinational logic, in order to perform the functions that we would like to have. A good way to specify a Moore-type finite state machine is to use separate procedural blocks for the three main tasks. The first of which is the next state combinational logic. So the computation of the next state based on the current state and the current input. And then the actual state update from that computation of the next state. We input that next state into the present state. That's the state update. And that's done in the flip-flops. And that's sequential logic. And then for the output, we need another combinational logic block which computes the output based on the present state. This is pretty much going along the lines of the block diagram of a finite state machine, in this particular case a Moore-type finite state machine. So we have here a Moore FSM. And as you recall, that's the distinction here is basically whether the output C is only dependent on the present state or whether the output C is dependent on the present state and the present input. Okay, so here we don't have a direct line that goes from the input W to the combinational logic that makes the output C. Here's an example that we're going to use to illustrate the ideas of how to put this into Verilog code. We look at the Moore-type finite state machine that reads a binary sequence W and sets C equal to 1 if either the string 110 or the pattern 110 or the pattern 101 is detected within the string, and we do allow overlaps. The state diagram of such a finite state machine is shown here. So this is a Moore finite state machine. And we start out in state A, which is also the reset state or the clear state. If we see a 0, then we stay in state A because 0 is not part of the strings we want to detect, which is 110 and 101. So to be precise, 0 is not a prefix that we are looking for. 0 is of course part of the string, but we need to have a 1 first. So we wait until we get the first 1, and then we go along this transition here. We're going to state B. If there is a second 1, then we're going to state C, so nothing happens yet. If we see more 1s, we loop around here. If we see now a 0 coming in, then we're going to state D, and we have an output C equal to 1 here. And if we see a 1 first and going to state B, and then we see a 0, then we go along here. And now we're hoping to see a pattern of the type 101. So if we see a 0 after that, we have to go back to the A state and start from scratch. But if we see a 1 after that, then we go into state F, and that also produces an output C equal to 1. And because we allow overlaps, if you are in state D, where we have seen a 110, if we see another 1, then we actually have seen also the pattern 101. Oh, that's one of those overlapping cases. If we are in state F, we have seen the pattern 101. And if we see a 0 after that, and then another 1, then we have another overlapping pattern and go back into state C equal to 1. If after the 101 pattern we see another 1, then we have seen 1, 1. And so we go back up here. And if that is followed by a 0, then we have seen 1, 1, 0. And so we produce another output here. So now the idea is to encode this in Verilog. Our first way of doing this is going to be the Moore 1 module. And here we do implement it in such a way that we have 3 procedural blocks, one for each of the main tasks, namely the next state specification, and then the update of the state, and then finally the assignments at the output. So we have inputs here, clock, just to run this as a synchronous finite state machine. We have an input clear with an underbar. That really means that we have a clear, which is negative logic. So if clear is low, then we are resetting the finite state machine. We have, of course, the input W, that's the binary sequence, and then we have the output C. So that's what goes high when we detect either 110 or 101. Then we have the state variables here, little y and capital Y. Little y is the present state, and capital Y is the next state. We have also used here the local parameter specification so that we can specify the states A, B, C, D, E, and F and make the code more readable. And what we do here is we just simply assign a particular bit pattern to A, B, C, and so forth. And we chose just to count up here 000, 001, 010, etc. And because this is called a local parameter, the local param, we cannot change those assignments from the outside, which makes sense. We do not really want to change the state assignments from a module that's higher in the hierarchy of modules. So now that we have the states defined, we can define the next state combinational logic that's done in this always block here. So this whole block here down to here, that just specifies what is the next state going to be depending on the current state. So the current state appears in here in the case statement, and then also depending on the inputs W, those appear here for each of the particular transitions that we are going, or those define the particular transitions that we are going to make from one current state into next state. So the A, B, C, D, E, and F here, those are the present state. And then the ones that we are specifying over here. Okay, so the ones that we specify here, those are the ones which are going to be the next states. So those are the next state specifications. And we just go along the lines of the state diagram that we have been making. So for example, if you are in state A and we see that W is equal to 1, then we go into state B because now we have seen the first one. If W, however, is 0, then we stay in state A because we are still waiting to see a first one. If you are in state B and W is 1, then we move on to state C. If you are in state C and W is 0, then we go into state D, and in state D, a little bit later on, we will see that then an output equal to 1 is being asserted. So we just simply have to go through and enumerate all the possible present states, and then write in terms of an if-else statement here what's happening if W is either 0 or 1, and then specify what the next state is going to be. So this does not yet make the next state happen. This is only just a specification of the next state. One thing that we should point out here is this last line here. The default of the case statement is set to 3 and then the dash b triple x. That means that it's a don't care. Okay, so this is don't care. And the reason why we need to do this is because with 3 bits we can define 8 states altogether, but we have only been using 6 states. And so there are 2 states beside those 6 that we are using that are also being part of what the Verilog compiler is looking at. And if we do not specify the default here, then there is no assignment for some of the 3-bit combinations, and that will make the Verilog compiler insert a latch here, and that would be a non-intended latch. The latch goes in here because Verilog, if there's no definition for a particular bit pattern, it needs to just keep what the previous value was, and that's why it puts a latch in there. So those are the kind of things that in the Quartus 2 compiler show up as unintentional latches. And so by specifying here for the default this don't care condition, that tells the Verilog compiler that it does not need to worry about that and does not need to put in a latch for keeping the content here of those bit combinations that were not used in the case statement. So once we have made the assignment or the specification of the next state, we can start worrying about the state update. So that's happening in this block here. This is the actual update from capital Y into little y, so from next state into present state. So that's actually done at this line here. And at this point, we're also providing the reset capability. So we have a sensitivity list here that includes the neg edge of clear and the pos edge of clock. And so if the clear is asserted, meaning if clear is low, then we set the present state to A, which is the start state. And otherwise, if clear is high, then we just simply take whatever the next state specification is and make it the present state. And then finally, we have the part that defines the output here. And we made it into an always block. We could have used just an assign. That would have worked as well. So if it's an always block, then the Z here has to be of type register, which is what we declared at the beginning. And what we're saying is just simply that if the present state is either D or F, then we set the output equal to 1. Otherwise, we set it equal to 0. And that corresponds to detecting those 110 and 101 patterns. Here is what the simulation of this module looks like. So we made a test bench which makes a clock. It makes a clear at the very beginning here. So the clear, it ends at this point in time here. And then after that, we're reading in whatever W is. So the W starts out with zeros first, and then there are 2 1s here. Then there's a 0, a 1, a 0, 1, 0, 0, 1, 0, and then a triple 1 here, and 2 more zeros. So we can see that after the pattern 1, 1, 0, which ends here, we get to see a 1 here in the C output. Then there is another pattern 1, 0, 1 here, so that ends here, and that makes another 1 output. Then there is a 1, 0, 1 pattern between this one, and this one here, and that makes an output here of 1. Then we see 2 zeros, a 1 and a 0 and a 1, so we get another 1 output here. And then we see a 1, 1, 0, so we get another 1 output here. Notice that there is a delay between detecting the 1, 1, 0 pattern. We could in principle have said that 1, 1, 0 can already be detected here. But the Moore finite state machine wants to see the pattern all the way to the end before it actually asserts then a 1 at the output. So we get a delay of 1 clock cycle here from the moment we could first have detected the 110 pattern. So this simulation here corresponds to the pattern 001101010010 11100, and we get to see a 1 after we have seen the 110 here. Then we have an overlap here at 101. We have another 101 pattern here. We have a 101 pattern here, and we have a 110 pattern here. And we can see that there is 5 such patterns, and we get 5 1s in the Z output. So here is a second version of encoding this in Verilog. We call this the Moore-2 module. And what we did here is we took the next state and the output specifications together into the same module. Both of those are combinational logic, and so we put those together into the same procedural block, not into the same module. All of this is in one module, but the next state and output computations are now in the same procedural block. So it's the same always block. So the definitions are the same as we had before. We have the clock, the clear, the W as input, the register C as output, and we have the 2 state variables, little y and capital Y. The state assignments are the same as before. And the next state specifications are exactly identical to what we had before. We use again a case statement based on what the current or the present state is, and then we also depend on what W is in order to specify what the next state is going to be. We have again also the don't care states, because we still have just 6 states that we use, but 3 bits, so that there are 2 unused bit combinations. And then inside now the same always block, so this is just one always block. Inside this block we now actually make the output assignments. Okay, so we have this portion here are the next states, next state assignments, and here is the output assignment. The same as we had before, it's just simply in the same always block now. This works because both of those are combinational logic, and so the sensitivity list that we have here is a sensitivity list that just depends on the levels of the signals Y and W, not on the edges of the clock. And then the state update, that goes into a separate always block, because here we have the sensitivity list is now the pos edge clock and the neg edge clear. That was the same as we had before, but this is edge sensitive, and you cannot mix edge sensitive and level sensitive statements in the or sensitivities in the always block. For this reason, we had to make two different procedural blocks. Okay, it's again such that we have asynchronous clear here, so the neg edge of clear. So here is where the clear is happening. And then we also have the update of the state. And that sets the flip-flops to the next present state. And here is a third version, which we call Moore 3, of implementing the same finite state machine. And in this case, what we are doing is we're taking the next state specification and the state update into the same procedural block, into the same always block. Okay, so here's how this works. We have again input, clock, clear, W, and C. That is the same as before. But now when we look here at the state variables, we only have little y. Okay, we don't have the capital Y, because we are going to directly update the little y from the current from the present state. We're going to make the next state and make this then the new present state. Okay, the state assignments here with the local param definition are the same as before. So now we have here this always block, which is sensitive to the negative edge of clear and the positive edge of clock. And we do the clear here at the beginning if clear is set to low. So this is clear as before, and the clear state is A as before. But now when we update, or actually when we make the new present state here, we do this by making the new present state and updating or computing the next state at the same time. Okay, so this is based on the current state. Okay, and if the current state is A, for example, and if W is 1, then the next current state is going to be B, and if W is 0, the next current state is going to be A, and so forth. So we basically bypass this capital Y computation by just making the loop around the flip-flops here directly update the state of the flip-flops. Notice that here it is crucial that we actually use the non-blocking assignments, because otherwise we're not getting the correct result. The non-blocking assignments, as you recall, take all the values as they are at the input or at the beginning of this always block, and then everything gets updated at the end of the always block. And so when we have the update of y here, that is actually going to happen in the correct way. Now the don't care states we also need here again, because we still have just 6 states, and we need to prevent the Verilog compiler from doing something based on seeing that 2-bit patterns are not being used. So we tell it explicitly that we do not want those to be used. Okay, so that is the update of the flip-flops. And then we have to make an assignment for the output. So this is the output C assignment. And here we actually now use an explicit assign statement. C is equal to, and then we use the conditional operator. So if what's in the parentheses here is true, then what comes after the question mark is going to be read into C. And if this is false, then what comes after the colon here, which is the 0, is being read into the variable C, or into the, it's actually not the variable anymore, technically speaking, it's a wire, because the assign statement has to go into a net and cannot be put into a register. Okay, another point to make here is that we could not have put the Z, the output statement for the Z, into the always block up here, because that would then have meant that C, because the block up here is sensitive on neg edge and pos edge, so it's one that's edge sensitive, and that would then have meant, if you would have put that statement directly in here, that C gets stored in a flip-flop first, and then only after it has been stored in the flip-flop, it would go into the output. And that would have meant another clock cycle of delay. We could have used a separate always block here and then make an always block that's level sensitive rather than being edge sensitive. That works in this case. The alternative to using a Moore-type finite state machine would be to use a Mealy-type finite state machine. And that's what we're going to take a look at here. We are going to detect again the patterns 1, 1, 0 and 1, 0, 1 with overlaps and set C equal to 1 if we see one of the two patterns. Now for the Mealy finite state machine, we're getting a simpler state transition diagram because now we produce the outputs as we actually go along the transitions between states. So we use the notation here that along the transitions, the first number that we show corresponds to W, and then there's a slash here, and then the second number corresponds to the output C. So if we go into state A, which is the state when we clear the finite state machine, if we see zeros, then we just loop around here and output the 0 because that is not leading to the detection of our desired patterns. If we see a 1, then we move into state B. We are getting closer to possibly seeing one of the patterns that we are looking for, but of course we haven't seen it yet, so C remains 0. If we see another 1, then we have seen the 1, 1 part, but that still isn't 1, 1, 0, so we leave C at 0. But then if but we go into state C. If in state C now we see another 0, so if we have gone like this, this, and this, then we have seen 1, 1, 0. So now we output the 1 here for C. And we do this on the fly as we make the transition from state C to state D. And then we could possibly output another 1 right after that, because if we see 1, 1, 0, and then another 1, then we see the pattern 1, 0, 1. So that's, if we go now this route here, and we see another C equal to 1 here, those are actually the two transitions where we see a 1 for the output. All others will make a 0 for the output. And then, of course, we can also detect here the pattern 1, and then a 0 and a 1. And so that will also produce an output C equal to 1. So now we just have 4 states. And we're taking a look now how to encode this in Verilog. Okay, so here is the Mealy 1 module. The input declarations and output declarations of the module are exactly the same as we had for the Moore modules. So we have a clock for the input, we have a clear, which is negative logic, we have the W, which is the actual binary sequence, and we have the output C here. We also use here the state variables little y and capital Y. So that is the same as it was for the Moore 1 and the Moore 2 modules. The local parameters, we have now fewer of those because we have fewer states, and in fact, because we only have 4 states, 2 bits are enough for making the state assignments, and we actually use now all possible combinations of 2 bits for the state assignments. And then we go into the combinational logic, which computes what the next state assignment is, or the next state specification is, based on the current state, and also then based on W. Now, based on W, we are actually going to make 2 things here. One is specify the next state. So, for example, if you're in state A, and W is 1, then we specify that the next state is going to be B. And at the same time, we're also saying that the output C is going to be 0 here, because now we have to specify both the next state specification and the specification of the output in at the same time, because we do this during the transition from one state to the next. Okay, so we do this for all of the possible states A, B, C, and D, and the all possible W's, so we get 8 different statements altogether here. We also note that we do not have any don't care states in this case. And that's just simply because we made our state assignments with 2 bits, and we have just 4 states, and we have exhausted all the possibilities here. And so there is no need to specify any states or any bit combinations that could have been states that are not being used. And then, of course, we have to do the update, the actual update. So that's done here using an always block with the negative edge clear, positive edge clock. And it's the same structure as before. If we see that clear is low, then we go into state A, which is our start state. And otherwise, we update the present state with the next state, and so the next state becomes the present state. Here is a simulation of the Mealy 1 module. And we can see here that we have the same bit pattern as we had before. We also have the clear here that is ending here. So we first clear the whole thing, and then we put in 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, and then all zeros for our W sequence. And the edges here of the W sequence are delayed by 1 nanosecond from the edges of the clock. Okay, so there's 1 nanosecond here in between. And we did that so that we do not have a change in W at exactly the time when we have a change in the clock, just to make sure that there is no ambiguity as to what the value of W is. But that leads to this little spike that we can see here, okay, because we are producing the output C on the fly based on what the current input W is and what the current state is. So because W gets delayed a little bit, so what we are detecting here is the pattern 1, 1, 0 is for that first C equal to 1, and then the next one is 1, 0, 1, so that's for the next part of C equals 1. But because W is slightly delayed with respect to the clock, we do not get to see that 1 here in the 1, 0, 1 pattern for 1 nanosecond, and that produces this spike here. So depending on what kind of circuit we are, or what kind of conditions we are working under, this spike could be a problem for something at the output. But if whatever takes the output is working on the same clock that we have here, then it would not get to see the spike because the spike is happening right after the clock has been happening. So this is one of the potential problems with Mealy finite state machines, that the outputs C, if can have glitches or spikes in them if the input W is not properly synchronized with the clock that's being used for the synchronous finite state machine. The benefit, however, is that we detect the 1, 1, 0 pattern immediately. So here we have 1, 1, 0. So the minute we see the 0 here, with the output C goes high. Same thing, for example, for this pattern of 1, 0, 1 here. The minute we see the second one, the output C goes high, and so we don't have this delay by 1 clock cycle that we had for the Moore state machine. Okay, so this simulation here corresponds to the W at the input being 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, and then the outputs come immediately here. So if you have 1, 1, 0, the output C is equal to 1 right here. Then we have the pattern 1, 0, 1, the overlapping pattern, so that leads to this output. Then we have the 1, 0, 1 here, that leads to this output. We have another 1, 0, 1 here, that leads to this output. And then we have a 1, 1, 0 that leads to this output here. So we detect things properly, and we detect them 1 clock cycle sooner than we would have done with the Moore machine.